So our 20% project is on energy, or world energy. So the consumption of energy is actually a lot bigger than you'd think. The entire world consumes 85 million barrels per day, which is about 3.57 billion gallons per day. So if you could, like for example, to sum it up, if you could somehow replace all of the water in Niagara Falls with oil, then you could let it run for 6 hours as 150,000 million percent.
This is the coal consumption in the U.S. It's in million short tons, which is 2,000 million tons. The actual consumption is shown by the solid green line, and the dotted green line represents future consumption predicted.
Now, over the entire Earth, we consume 144 sextillion, 484 quintillion, 20 billion, some number like that, watts. And a watt is 1 joule per second, so that is over a year. So with this power, it's a bit insignificant, but we could power a light bulb, a single light bulb, at your average 100 watt, for 45,785,215 and a half years. That's a big number. Now there's also renewable and or clean energy. Now some would protest against clean, but it's technically renewable. Now there's biodiesel, which we use about 250 million gallons per year in the U.S., and there's the much more popular ethanol, which has derived from alcohol, and we use that 5,400,000,000 gallons per year in the U.S. Now there are also fuel cells, but it's not very consistent measuring them because you can buy it in any store and it converts a chemical reaction between one gas and another as a catalyst, like for example hydrogen and oxygen, and makes electricity out of it. So for example, alkaline fuel cells are one of the most popular out there. There's also hydrogen fuel cells that are coming to the market, but we'll see about that. There's also phosphoric acid fuel cells, which are kind of popular-ish, and there are a few others that are not. Now there's natural energy, which people are very hyped up about because it's clean and yeah. So geothermal, we take about 3.1557 times 10 to the 17th joules per year is how much is produced. Hydroelectric is 2.2 times 10 to the 19th per year. Solar is about 2.4 times 10 to the 17th per year, and wind is that big one.
2.8 times 10 to the 15th.
Thank you, math teacher. Now, nuclear fusion. Now, this might sound unclean to you because nuclear energy, cancer. But nuclear fusion is different from nuclear fission. You see, nuclear fusion takes light elements, which are lighter than iron, and they combine and make energy. So, for example, you take a bunch of hydrogen, or the deuterium and tritium, or deuterium, tritium, 2 and 3, and you combine them with fusion to make helium. And then that immediately decays into another helium and a single neutron.
With a total of 17.6 mega electron volts.
Boom. Go back. So, heavy elements separate and release energy, which is fission. Now, fission is what is customarily used in nuclear reactors, which makes radiation. Now, you hear a lot about uranium because it is the heaviest natural element produced in nature. So, when used in fission, then you can harvest a bunch of it, and it's very heavy, so it makes a lot of energy. Basically, it's the most profitable, and energy-wise, profitable elements that you can use in nuclear power. Now, nuclear fusion isn't very, well, it's not very widely used, and it's not that efficient right now, because it just doesn't work very well. We haven't figured out how to use deuterium and tritium efficiently enough so that it makes a profitable amount of power, because it takes a lot of power in the first place to combine these two elements, or isotopes, and there's just no energy profit at all. At least now, at least. Now, what else? What else is there? What else can you do? Well, you can turn off lights when not in use, open window not using AC, etc., etc. And make one of the things that we made. Where are you going? What are you doing? So our engineer friend here made a little gadget that it's very simple. It powers little LED lights, but the basis of this is shown on the board. This is a little dynamo generator, which means that the spinning crank turns magnets with mechanical energy, and magnets rotate around or inside a copper coil, and then the copper coil creates and then that creates an electromagnetic field, which, as you know, electric. Now, as you can see, this is lighting up because we're converting mechanical energy, or my arm moving, to electrical energy. Just like the more mechanical energy, the brighter it gets, because it's getting more energy.
Charlie, can you do that again for us? Because I moved it around Peter. Thank you.
As you can see when I turn it back now, it's brighter. If you can hold it up against the wheel.
And then if you get too fast, it's just like bang.
Over the wheel.